watts. So what's going on? What's in the light bulb? It's an assembly that happens to have mirrors, reflectors. So if you had a filament doing its normal job, it would radiate spherically. It would be like a globe. It would radiate from a point in all directions. And what you really want is a beam that's, who knows, I don't know what it is, it's maybe about 30 degrees in both the vertical and the horizontal plane. And so you really want this box of light to hit the ground. You don't want to go out and hit the guy unless you're out in the country and you have your high beams on. You want it to hit the ground maybe 300, 400, 500 feet in front of your car. So you can light up the area where you're going and not bother anybody else who's coming in your direction. Well, instead of radiating spherically, you're radiating in a narrow path. All the light that's going in that narrow path includes light that was going out in that direction but hit a mirror and bounced back in that direction. It got focused, it got concentrated, it got scrunched into a small space. That is exactly what antennas that look like this. They have a boom, they got multiple elements in it, and tend to do. If you were to look from the top down using a polar coordinate chart, if you had a dipole, it would look like this. It would have two lobes that they call cardioids. They're called cardioids because there's actually a little dimple down at the bottom. It's sort of like a heart, not much, but a valentine. Not much of a point here, not much of a dimple here, but they, close enough they call it a cardioid. And that's the concentration of energy. Almost nothing goes off to the sides. The maximum goes off in not two directions, but it's actually a rotation. It's a whole cylinder of radiation pattern going in a circle like that. And there is actual gain over a spherical radiation pattern. A spherical radiation pattern really can't do because, again, an antenna has to have a certain physical length. If it has a certain physical length, it's not a single point. Point being something without dimensions. Remember that from geometry? Therefore, we have a theoretical thing called an isotropic radiator, which is that single point, which doesn't exist, but it's a starting point. When you have this thing called a dipole, I'm not sure, I think it's 2.1 decibels of gain. And I should talk about decibels in the next session, I will. We're going to get into just a smidge more math. I'm going to talk about what decibels really are, what binary number systems really look like, and things that only they can explain to you because they will be on the test if you go to general or extra. There's gain. There's a multiplying effect. 2 dB is, like 10 squared, so like a factor of, well, I can't say a factor of 100. A factor of 2 is 3 dB, so that's, it's a little gain. It's maybe not double, but it's at least half again as much. Then you get just from a simple diode over this isotropic. What these guys are doing with these multiple elements is they're narrowing that beam. They're producing, ultimately, a beam that looks like that. There might be a little bit going the opposite direction, but this thing is really narrow. And if you get the one I'm looking to buy next year, a TH11 DX made by High Gain, and works on everything from 20 megahertz, 14 megahertz up to 30 megahertz, meaning 20 meters up to 10, which covers about 5 bands. The gain on that thing is 21 dB. If you do the computation, you divide by 10, you take that to the power of 10, it comes out to about a multiplier of 158 times. That antenna will actually not only take your 100 watt signal and make it look like it's 1,058 watts, but when you receive signals from other people, they'll get the same treatment, they'll get the same gain factor, they'll multiply. be multiplied in similar ways. So the emphasis is always explained to hams. If you want to get a linear amplifier, buy a good antenna first. You may never get around to buying that linear amplifier. Some of the best people we know in our club that have racked up 100 countries on every band and keep going more and more. In fact, Don Whiteman wrote this cute little experiment. He did only a couple of weeks ago. There was a DX contest on the air. And he said, I wonder if I could, the propagation is so good, I wonder if I could work 100 countries in just the morning alone. Started at 8 o'clock. By the time it was over, there were ups and downs in the process. He had 102. Now this is an award people sometimes spend years trying to get. He got it in 4 hours.
With 100 watts.
With 100 watts. And a vertical antenna, which isn't necessarily the highest gain antenna there is. A vertical antenna is a quarter-wave radiating element. The counterpoise is the earth underneath it. And he did that well. Power isn't the answer, the antenna is. And if you had a better antenna, what can I say? So what I'm spending my money on in my retirement is putting up a mast that's going to have 4 antennas on it. 3 of them will be beams, and 1 will be a stacked array that's used for satellite tracking, which requires some really high gain, but it's on a narrow set of frequencies, so it doesn't, and it's very high frequency, so it's not that big. And you can spend 10, 20, even 30,000 to do it, but hey, that was my goal. I haven't done it all these years because it was so costly. Most antennas like that one, if you put it on a tower with a rotor and, it goes up 20, 30, 50 feet, it can set you back about 10 grand. Because you have to dig a hole in the ground, you have to fill it with rebar and concrete just to stabilize it. Or you can run guy wires if your neighbors don't mind, or your wife is not too fussy about, the aesthetics of the house. It's another reason I'm doing it now instead of earlier. My wife had passed away in 2011, said, you're not going to uglify the house. I married somebody a year and a half later, and I told the club during a banquet, well, he says, it's okay for me to put up a beam antenna. The whole audience got up and said, yeah! And Don Wakeman said, now you know what the values of this organization are. Elevation and antennas that produce gain. Now, an antenna, again, is a passive device. It doesn't have an amplifier in it. It produces a multiplication of signals simply by doing tricks to concentrate all of that stuff in one direction. And what you see with these multiple elements is basically this. You got one driven element, and then you might have a thing in front, and there's a certain amount of circuitry that cross-polarizes these things, and then actually this is the one in back, this is the one in the center, and this is the one in front. One in front might be what they call a passive element, a parasitic element. It receives the radiation from here, it takes that, and is energized by the radio waves, and then in effect, retransmits it. It's like a capacitor. You put energy into it and it gives it back. Except it's doing it by its very length and its very spacing between the 2 elements, so that it helps to narrow down that signal and give you gain. This guy's called a reflector because the power going that direction gets bounced back and made to go in the opposite direction. These things with these multiple elements are called Yagis, named after a Japanese engineer that came up with the concept of beam narrowing by the process of using multiple elements. Another way to do it is you have a parabolic reflector and your antenna's in the middle. And you know what it is with the parabola, everything, no matter what angle it strikes the dish, it's going to come out as parallel lines. That's going to really focus a pencil-thin beam of energy in one direction. The problem is this thing's got to be relatively smaller than the dish. So that works great at microwave frequencies. At the lower frequency, your dish would probably be the size of a city block, and your neighbors, again, are going to have problems with the building permits. So that's what they do when they try to pull radio signals from space, or they have link-ups to satellites or the International Space Station or people in orbit, is to multiply the signal by putting a parabolic reflector behind it. The antenna is actually this feed horn in the sun, in the focus location of the parabola. The rest of it's just a reflecting surface to concentrate the energy. You see that all the time. People with DirecTV or Dish have what? An 18-inch antenna. If they want to spend a little more money and get a little more gain, they can put a 24-inch one up. But the feed horn, actually, this isn't at the focus. It's a little below the focus, so it can receive signals coming from above more easily. But it's designed to work like it is parabolic. And sometimes it's elliptical because they're pointed at two different satellites in space, and what they have is with an ellipse. Ellipse has two foci, and as long as the satellites are on that axis, they'll all get the reflection of the panel behind, and they'll all be concentrated in the antenna in the middle. Look at any of these cable TV operators who have sometimes just one dish. Go down where in Highland Park is it? You get off of 41 at Deerfield Road. It's not Clay, it's Deerfield. And I think just south of that is where Comcast, formerly US Newsweek cable, when it first started out, has one dish. And it receives all these different satellites at different orbits. Now, the orbits are all in a straight line because they all have to be over the equator to be synchronous. But this one dish can pick up all these different satellites because it's elliptical, and between this focus and that focus, anywhere along the line, the signal will bounce back to the antenna. That's another antenna design. You've seen the antenna design that you have in the car. You may have a loading coil, you might not, but the counterpoise is the body of the car. That's the configuration. This guy could be either quarter wave or with the effect of the coil, electrically a quarter wave. The coil will electrically lengthen the antenna. Configurations for antenna are many in number. You see vertical antennas a lot. And they put coils, actually tuned circuits in them, and what they do is they make certain parts of the antenna block signals. These are actually low-pass filters. So if you're operating at a low enough frequency, the whole antenna is lit up and it's a quarter wave. If you're operating a higher frequency, a certain part of it is blocked by this thing called a trap, this filter, and the antenna is shorter. And at a higher frequency, even shorter still.
Is that how you do dual band and tri-band antennas then?
These multiple band antennas, if you look at the elements themselves, you'll see lumps, coils in them that electrically block the signal from going any further. They define where the new endpoint is. A signal lower than that frequency can pass through. At the higher frequencies get blocked there, and that shortens the element so it stays resonant at the band of interest. If you want to see the ultimate application of that, look up the stepper, S-T-E-P-I-R. The big IR at the end. What they have is polyvinyl tubes. They got a motor here and unwinds a piece of wire, literally extends and contracts a wire and makes the radiating part inside the antenna the exact length it's supposed to be for the frequency of interest. Boaters, you'll see, have these fiberglass antennas in their boats. Well, that's not what's radiating. It's a piece of metal inside. Fiberglass is just to keep it weatherproof. So the part around it's called a radome. Anything that surrounds an antenna is transparent to radio signals is called a radome. You see that with the weather stations with the microwave antenna spinning around inside it, but you don't see it. You get to see this big white ball around it. It's made of a polycarb material that essentially is transparent to radio waves, the frequency of interest. But the thing about a vertical antenna is this. The signals radiate from the antenna pretty parallel to the Earth. So if you're trying to reach somebody at a very distant point, here's your antenna, your signals are going out parallel to the ground. They will go the farthest possible distance before they reach this belt of ionized particles above the Earth called the ionosphere. The ionosphere has charged particles. And what charges them is the sun's radiation, which makes the electrons detach themselves from their nuclei. And when they become ionized, they become radio barriers at certain frequencies, lower frequencies in particular. The thing about wanting to get a general and extra class license is that without it, you cannot operate below 30 megahertz. Below 30 megahertz, or 50 more specifically, the signals will reflect off the ionosphere and come back down to Earth many, many miles away, sometimes on the opposite side of the globe. Or they'll bounce several times. They'll go out, hit the ionosphere, bounce back, go out, bounce back. They lose power every time they do that, but having a low launch angle means you're going to send that signal out farther. So what's interesting about a vertical is it has that low launch angle. What's bad about it is it's a dipole. It doesn't concentrate the energy that much. It's only got about 2 dB gain. So you don't get the gain factor, but you make up for that in other ways. So what you choose depends on your interest. If you have a Yagi, or we tend to call this thing a beam antenna because what it really radiates is just that narrow beam, you have to rotate it. You have to spin it around, point it in the direction that you want it to radiate, and the other directions won't necessarily hear you or you won't hear them as easily. So it's a little bit more of a hit or miss situation, but when you find a rare station on the other side of the Earth, that baby is going to really pack a signal going out, and you'll really suck it in coming in. It's going to. That's how you get the big jet, the big catches. Is they have that kind of equipment, which is why I'm trying to build one. Okay.
What about log periodic?
Oh, good one.
I picked up one a while back.
Yeah.
It's kind of
Well,
interesting.
Log periodic is generally used at higher frequencies. They actually, Highgain made one that would go all the way down 40 meters, which is 7 megahertz. Boy, that thing was huge because of the way they work. But where you have seen a log periodic a lot is TV antennas. In the days when we used UHF and VHF,